This is the last lesson in Chapter 8. The first part of the lesson focuses on solving for missing coordinates for different types of quadrilaterals. And in order to do these problems, we either need to graph them or sketch a picture. And we also need to understand some of the basic properties of quadrilaterals like parallelograms, trapezoids, isosceles trapezoids, and kites. First couple of problems are pretty straightforward. You're just going to plot the point just to get used to this idea of solving for a missing point. It's a good idea to label your points because based on the naming I need to go around in a circle. So here I have 2 of the 4 sides of my rectangle, and really all I need to do is just eyeball where point D is. Point D is going to have the same y value as A and the same x value as C. That's another way of finding what that ordered pair is, but I like graphing it best. Number 2, this time we have a square. I'll start to shape it out. Here are the diagonals, or part of the diagonals of the square. And I know the diagonals in a square do everything perfect. They bisect the angles. They bisect each other. They're perpendicular, which means that in order for this all to happen, point D needs to be at 0, -4. Let's go down to the isosceles trap one. So I can already tell that the last side is going to need to look something like this in order for there to be exactly one pair of parallel sides, which is the definition of a trapezoid. It also says that this needs to be an isosceles trapezoid. And if I remember back to when we talked about trapezoids and we found area of isosceles trapezoids, we always had this right triangle that flanked the rectangle inside that was congruent to the right triangle on the other side. Or in a sense, I have this slope that I just need to count off in the other direction to find where point D is, so that this looks like an isosceles trap. This isn't really an exact science. I'm just graphing it, plotting, sketching it off, and my ordered pairs on problems like these need to be integer value ordered pairs. Do this parallelogram one. And with that same idea of the trapezoid, because trapezoids and parallelograms, although they're not the same, they do involve parallel sides. So I know that the other side of the parallelogram is going to lie somewhere on this line. I'm going to use that idea of slope again because opposite sides are parallel. So I'm just going to count off this triangle, but sort of count it off backwards. It just so happens that D lines up right where that other right triangle's right angle was. That doesn't always happen. And it's at, D is at -4, -5. Let's look at another one. Let's do another parallelogram one that's not so easy and maybe a little more spaced out so you can see a little bit better about how this right triangle works. So here are the first two sides, first three vertices. Here is the third side, and here is the right triangle that I'm going to try and copy over here. I'm going 1, 2, 3, 4 units to the right, and it's easy to figure out how far up I go. That's point D, which is at 6, 7. Let's go to the ones that involve variables. With the variable problems, we don't want to use any new variables. In addition, with the variable problems, we want to keep in mind that points that lie on the same horizontal line have the same y coordinate, and points that lie on the same vertical line have the same x coordinate. And the other thing is quite frequently when a picture is given, they label that these are the x and y axis. And sometimes one of the points lies at the origin to make it a little bit easier. And it wants me to find the missing coordinates for the points. Well, I know where O is. I probably don't even need to waste my time finding that. I know that Z is at the same x position as this point A comma B that they gave me. So this is going to be at A comma 0. And W is at the same vertical position as the point that was given, which means this is at 0 comma B. There are my two answers. Number 8, I'm going to have a rectangle. This one they require that I sketch my own picture. It's almost better not to do this on graph paper. AB lies on the x-axis, so B will be over here. C is at M comma N. This will be D. I'm going around in a circle. These are of course all right angles because it's a rectangle. And the other reason I want to put C out here is that based on the fact that it's M comma N, it's probably best not to have it lie on the axes. This really won't work out if I do that. This is really the same problem as the last one. It's just that I had to sketch my own picture. There we go. Let's look at this isosceles trap one. The isosceles trap, they give me this left vertex, the other left vertex, the right vertex, and I want to find Z. So that means that these are equal, that these are equal. This is of course a right angle because that's where the x and y axis meet. And I want to give directions to Z. So to get to this point over here, we'll call it X. I went left B, which means that to get to Z, I'm going to go right B. And also I noticed that point Z is at the same vertical position as X, which means it's B comma C. Let's go down to the rhombus. I know that a rhombus has perpendicular diagonals, that they bisect each other, and they also bisect the angles. I don't know if all of this is necessary to mark, but it's good to remember all of these because in some of the more challenging problems you do need to use this information. So that means that to get to this point, I traveled to the right A. To get to W, I'm going to travel left A. To get to the top vertex, I traveled up B. To get to Z, I'm going to travel down B. And then 12 gets a little bit harder. I have a parallelogram. I want to find W. And as the problems get harder, I really like to label things. Like, for example, I traveled right to this point, A units in length, which actually means that this also measures A because opposite sides in a parallelogram are congruent. the other thing that's sometimes useful is to draw in this rectangle, sort of like a slope, sorry, not rectangle, right triangle, sort of like a slope right triangle, because this is right B, and this is up C. So I can now think about how to get to W, and I need to travel to the same vertical position as this top left vertex. So this is going to be C. And I need to travel all the way over, which means I'm going to be traveling A units, and then this right triangle here is the same as the red right triangle, meaning this is B, and this is A plus B. So if you're finding yourself stuck, label your picture extensively like this. Mark congruent pieces up, label congruent pieces, and see if that doesn't help you find the missing point or the ordered pair of the point or points. The last part of this section, as I hinted in probably some of my other lessons and in-class discussions, is really going back and reproving theorems from previous chapters using the coordinate plane. There's no way we would have the time to reprove everything, but we will pick certain things to go back and prove, which offers as a great reminder to some of the big ideas that we learned in this course. So we want to prove that the diagonals of a rectangle are congruent. Quite frequently, the picture's already drawn on these, but on these problems we're going to draw out a picture together. The book problems that are like this, they have a picture drawn. And if you're going to draw your own picture, you want to place one of your points at the origin to make it easy on yourself. The other thing that you want to do is you want to use the least number of variables possible. Meaning, if I call point B 0b, like lowercase b, then C would have the same y value. I don't want to use a new variable for C. And then for D, I might call it D comma 0, which means that C is at D comma B. If I just create all new variables for all of the points, it's not going to work. And the reason I'm doing this is because I'm using the properties of a rectangle, that these are all right angles. So I have vertical and horizontal sides because I started my rectangle at the origin. And what I'm going to do is I'm going to find BD, which is one of the diagonals. So I'm going to use the distance formula. I'm going to simplify as far as I can simplify. That's actually as far as I can simplify. Then I'm going to do the distance formula for AC. It's always fun doing this when one of the points is at the origin. And what I've done is I've proven or visited the fact that the diagonals are congruent in a rectangle. So these two quantities, which can't be simplified, are in fact equal. We'll go to a slightly harder one. This time we'll go to a rhombus, and we're going to try and prove that the diagonals in a rhombus are perpendicular. The figure's going to get just a little more complicated. Again, I'm going to pick one of the points to start at the origin. I'm going to put B at B comma 0. I'm going to put D at D comma C. And I know that point C is going to have the same vertical position as D, and to get to C, I'm going to have to travel right D units, and I'm also going to have to travel this distance, which is B units, because that's how far this is. This is B, and this is B. So this is B plus D. I had to use more variables here because I don't know the type of lean that I have with this rhombus. A rhombus can have a variety of leans. The only thing I need to have, though, is fix my marking. All four sides congruent. So I'm going to find perpendicular deals with slope. So I'm going to find the slope of AC. I'm going to find the slope of DB and these don't look perpendicular. So I need to go back and kind of think about one of the boxes or theorems that we wrote out about perpendicular lines. I also said that the product of the slopes should be -1. This would be a situation where I might employ this trick because I don't know what else to do, and I don't want to just plug in values for C, B, and D, because I would in theory have to do that for every number imaginable. So I end up getting C squared over, and when I FOIL out the bottom, because this is just a difference of two squares, this is really D plus B, probably would be better to write it that way. It's D squared minus B squared. That sort of helps, but not really. I'm still kind of stuck. So I'm going to go back to my figure, and right here I have a right triangle. The vertical leg is C. And all of the sides measure B. I was thinking there for a second. Okay, so I'm going to do Pythagorean theorem, which is C squared plus D squared equals B squared, the hypotenuse. And I'm going to solve for C squared. C squared equals B squared minus D squared. And I'm going to plug this in back over here. Okay, so I've got B squared minus D squared over D squared minus B squared. And there was this old algebra trick of factoring out, I'm running out of room, of factoring out a -1. So -1, D squared minus B squared. You can factor it out of the top or the bottom. I'm going to factor it out of the top, which means I'm not going to touch the bottom. Now I can cancel these, and I see that it's -1, which means that therefore the diagonals are perpendicular. So I've reproved that the diagonals in a rhombus are in fact perpendicular through this process using the slope formula and the idea that if I multiply the slopes and I get a -1, they are perpendicular.